should begin. This is not the first Dalgarno lecture which Jun Ye is giving. The first one was yesterday in the physics colloquium, and as far as I understand, there are now people in Jefferson 250 also tuned in to Jun's second lecture. It's a pleasure to, for at least those of you who have not been to the first lecture, to introduce Jun Ye, who is a professor of physics at the University of Colorado, is a NIST fellow and a JILA fellow, among many other honors, which I will come to briefly. Jun graduated from the University of Colorado, working with Jan Hall, and then after a stint at Caltech, came back to Colorado, where most usually people end up, where he has been since, and doing, a broad spectrum of atomic and molecular optical physics, precision measurements, and sort of perfecting instruments such as the optical strontium optical clock, which I think has been sort of mentioned is the most accurate device that humanity ever created. So, and he may mention the level of accuracy. He did so yesterday in the lecture, first lecture. But today he's going to talk about molecules under the new light. I should mention that his group, with Debbie Jun's group, were the first to cool a molecule to its absolute ground state, by which I mean translationally, electronically, vibrationally, and rotationally in its absolute ground state. And of course, they've done many fantastic things with it. And Kan Ni, who was the original author, she's now on the faculty in the chemistry department here. Jun has been sort of a recipient of, I would say, at least that many prizes. And I counted this morning, there were upwards of 30 or so more. I'm just going to name a very few of them. He won the Breakthrough Prize for Fundamental Physics, Vannevar Bush Award from the NSF, the Ramsey Prize in 2019, the Robbie Prize in 2007, and as I said, many gold medals from the Commerce Department, which sort of celebrates the achievements of a scientist. He has 4 patents under his name, and the last I counted, he had more than 40 Science and Nature articles to his name published. One of the measurements that he and Eric Cornell are doing at JILA on this measurements of the bounds on the electron electric dipole moment. The standard model says that the electron does not have a dipole moment, and try to sort of find ways to distinguish this dipole moment, sort of tests the physics in the 10 to 50 TeV range. He may say something about. So without further ado, I should also, before that, I should mention that his third lecture, last lecture, would be on Thursday in Pierce Hall at 10 o'clock in the morning. Without further ado, please, Jun.
Thank you, Hussein. First of all, thank you very much for the great honor to come to, I guess, Alex's home, to give a lecture in his honor. And I very much feel, excited, but also humbled to give this lecture in his name. I never had a personal learning from Alex directly, but I have had dinners with him on social events, and I always found incredible person to have a conversation with. But more importantly, the literature of what he's set up are, as you can tell from this field of molecules, Alex was really the one who kind of kick-started the whole field. So I'm going to go tell you a story about molecules today. And let me just give you some interesting, I know that Mike was encouraging me saying, don't be worried about talking about molecules, even though I'm giving astrophysics kind of a colloquium. So I'm going to tell you about the molecules. And give you, I'm not a chemist. So my perspective will be very physicsy. But nevertheless, I feel the boundary between physics and chemistry really should be blurred. We are all using molecules to do some new interesting science. And that's the most important part. So I will tell you a little bit of a few stories, and hopefully you will find this interesting. By the way, the title of my talk, I switched a little bit, and it was after consulting with our director, and Hossein was telling me, if I talk too much about spin models, perhaps that's more fitted for a lot of the theorists in Harvard. And here should be talking more broad scope, sort of a molecular science and applications. So I want to touch on a few topics. In fact, Hossein actually introduced this, and how to use molecules to be a probe of the fundamental laws of nature. At the lunchtime, we were joking about comparing experiments at the sun, where you build accelerators trying to discover new particles, versus you do super precise measurements using atomic molecular systems and try to tease out with high precision the fundamental symmetry violations in physics. Do we have physics beyond the standard model, as an example? Since we have a lot of mysteries still in the universe, astrophysicist is telling us about it. I also want to touch on a little bit about complex structure and interactions. This is almost in honor of Brian Changala, who is actually in the audience. That was his PhD effort. And going beyond, I'll tell you a little bit of the most recent, very, very surprising discovery of some of the symmetries and the quantum statistics and so on at play when you have 60 bosons working together as you can see as a soccer-shaped molecule of following molecules. And I also want to shed light on a little bit what Hossein said. When we were able to cool molecules down to the absolute ground state of all degrees of freedom, now you can start to think about building a quantum systems from scratch. Molecule one by one, you can put them together in optical lattices, and you can use this to tune with electric field, with microwave field, and so on, and look at the complexity and the complex quantum many-body states coming out of these long-range dipolar molecules. My hope is to give you a flavor of all of this and hopefully going through in a very coherent way to tell you the story about this. So let me start with science with cold molecules. As I mentioned earlier, if electron had carried a dipole moment, it would immediately violate the so-called time reversal symmetry. Because as you can see, the electron carries a magnetic dipole moment. You can think of as a fictitious current running around the loop. And if it also carries a electrical dipole moment, you cannot have, if you reverse against parity or reverse against the time, you cannot satisfy both without reversing the directions of one of the dipole moments. Therefore, electrons are not supposed to have a dipole moment, or at least in the standard model, actually says electron dipole moment will be at the level of 10 to the minus 38 electron centimeter. And so how do we, on the other hand, we feel like there's a big greater mysteries of matter-antimatter asymmetry and so on. So perhaps physics is calling for a stronger CP violation or time reversal violation. And you can do experiments with molecules, such as this. If you have a diatomic molecule, you can apply electric field. The molecule will be oriented along the electric field. You can do find a parity states where the molecule can be aligned or anti-aligned with the electric field due to the doublet structure that you have in the molecules. And inside you have electron, which has a spin. The spin can be aligned along the electric field or anti-aligned with the electric field using the magnetic field to control that. So by switching electromagnetic field, these are laboratory fields that you can control the orientation. You can actually look at the possibility there's a frequency shift of electron when it's aligned with electric field or anti-aligned with electric field, while you can suppress away the magnetic field-induced systematics. So these kind of differential measurement techniques will allow you to set new bounds of the possibility of the electron actually possess an electric dipole moment. And these techniques are being pursued here in the Acme collaboration, which is on Harvard in John Doyle's lab in collaboration with Dave DeMille and Jerry Gabriels. And it's been going on also in JILA in Eric Cornell's laboratory where I participated. So if you look at the history of EDM search, again, this idea actually came out of Cambridge. Was Norman Ramsey and Ed Purcell. They started this idea that let's look for a possible very tiny moment of fundamental particles that will tell you about the symmetry of the universe. And so you can see that initially people were setting bounds of the possibility of electrons, electrical dipole moment. It was atoms. But around 2008 or so, the era of molecules started. And the molecules have this tremendous advantage that electrons is subject to a very large intramolecular electrical field, which will amplify the energy shift if the electron dipole moment is aligned with electrical field or anti-aligned with electrical field without having to switch with a very large field in the laboratory. Because oftentimes when you switch a large electrical field in the laboratory, you induce a lot of systematics. So that's the whole point of the molecule gives you this huge leverage of having this intramolecular electrical field to look for this tiny energy shift. And this has been going on. For example, you look at Imperial College, this ACME experiment here at Harvard. Now recently, I think the experiment generation 3 is moving to Northwestern University and at JILA. These are, the best limit is now placed at about 4 times 10 to the minus 30 electron centimeters. The reason why I bring this up as a first discussion is, well, all these techniques relying on control of molecules, in fact, relying on very traditional physical chemistry techniques, such as photoionization. When we prepare these molecular ions, in this particular case, we use hafnium fluoride ions. We do rotational vibrational pumping, optical pumping, so they can mix all these rotational states with a microwave. You put an optical photon that you're pumping all the states out of irrelevant sort of a ground state onto through some optical pumping dissipated with photon loss, and eventually the population gets coming down to here. You can actually put all the populations in this so-called science state where the vibration equals to 0, rotational level equals to 1, and you can see this triple delta 1 state features the so-called doublet states where you can have a molecule oriented with electric field or anti-oriented with electric field. So you can do that electromagnetic field switching that I was telling you about. And you can also do spin polarization. So throughout this technique, using photoionization, optical pumping, molecular orientation, spin, these are the techniques that's been developed over the years in physical chemistry. And we use this technique to do state preparation of molecules. I just want to tell you these kind of connections where physical chemistry tools can be becoming a really useful tools in fundamental physics. The other thing that I want to mention, another very familiar techniques, photo dissociation in physical chemistry, in molecular science, people use orientation mapping. In our particular case, you can actually say, I'm going to create a coherent superposition of spins up and down in those states. And I want to read out the population of these ions, how much ion are in the up, how much population are down. I'm doing this electron resonance spectroscopy after I create coherent superposition. I want to see how that's evolving, because that tells me this little tiny energy shift of the electron dipole moment. And so the technique we use is that we photo dissociate ion into products, but we can do it in a way that when the molecule is oriented with electrical field, when it's dissociated, the product flies to the left. If the state is anti-aligned with electric field, when we do photo dissociation, it flies to the right. So just by doing this mapping, orientation mapping, we can actually directly map quantum state populations into sort of left-right population counting. And this allows you to do normalization where even though the molecular number might be fluctuating, but when I normalize things away, I can get to the so-called quantum projection noise limit. Meaning, if you have this state in superposition between ground and excited state, when I read the population in the excited state or ground state, there will be noise associated with the quantum uncertainty of the projection. But if I normalize things, then I can remove all the technical noise and actually limit myself to this fundamental quantum projection noise limit. in the future, you can even think about spin squeezing, spin entanglement. But this alone already allows us to get a fantastic signal-to-noise ratio. This almost like a theorist's calculation of a fringe, of a Ramsey fringe. But it's actually real experimental data. It looks just fantastically nice. The reason why you're seeing some sort of a beating actually reflects the fact that we prepare molecules both in the excited state and the ground state, and it created this coherent superposition. And we can read out both this manifold and that manifold simultaneously, and they have a slight different Lennard G factors and so on that allow you to see coherent superposition of two quantum superpositions beating against each other, and that shows the beat signal that we can detect. But the point I want to make is through these, in some sense, traditional techniques that we have in physical chemistry, you can do this very precise electron resonance spectroscopy with this incredible signal-to-noise ratio over a very, very long coherence time. Here shows about 1.5 seconds. Now we have data going up to 8 seconds and 10 seconds. And this really is the reason why we can set such a tight bound on spectroscopy resolution of detecting possibility of electron electrical dipole moment. So once you talk about optical pumping using photons to redistribute the population in the molecule rotational states and so on, once you can do that, you very quickly start to realize, oh, I can actually do photon cycling, meaning if I can put all the populations to a particular quantum state and I can keep cycling that photons back and forth without moving these molecular states to other dark states because I can optically pump them back. If you can start to do a photon cycling, that means each photon hits on the molecule will have a recoil shift on these molecules. And that means you can start to have a mechanical actions of a laser cooling these molecules. And this is the field of direct laser cooling of molecules, therefore, is very much connected to all these photo manipulation of the molecules. And this has now become a vast research field. How do we make molecules, laser cool them down to very low temperatures so we can create a quantum gas of the molecules? Not quite there yet with direct laser cooling, but there are techniques where it's coming up. For example, just down the road in the joint laboratory of Doyle and Conquin, and in collaboration with Wolfgang Ketterle, they have now created an array of tweezers that's filled with molecules. Doyle's lab has also been pioneering the work of even polyatomic molecules now, as certain select species can be laser cooled. And that really feels very much chemistry kind of a molecule that John Doyle's lab is able to bring under control to very low temperatures. And that's very exciting. In my own laboratory, we have been cooling a diatomic molecule called yttrium oxide, YO, and we have reached actually the highest phase space density. And you can look at it, the molecules being cooled down to very, very tiny spot. The tiny spot is not important. The importance is the temperature is now at a few microkelvin, starting from room temperature, starting from actually nearly hundreds, thousand kelvins, because we have to laser ablate them and so on. And now you start to think about experiments that's becoming possible with such large phase space density. You can start to think about doing evaporation of these molecules. The first thing you can study about collision, that Hossein, our director, is a true expert, leading expert on this. When the temperature gets this low, you can actually start to think about, well, two YO molecules, they are bosons. When they come together, if they are identical bosons, they will have S wave or D wave. They cannot have odd partial waves because the bosons have to be symmetrized when they exchange positions. And so when you have a spin polarized YO molecules coming in, they will collide through the S wave. This is the van der Waals potential with no barrier. But if you have a mixture of those spins, if they are non-identical particles, they can collide both through S wave, P wave, D wave. Those are partial waves according to the relative angular momentum between the two molecules. So you can have a spin mixture, which for the P wave, we have these so-called centrifugal barrier, 5 microkelvin. If the temperature of these molecules are prepared at a few microkelvin, well, these barriers make a difference. The P wave, whether they can tunnel behind or not. And you can see directly, with laser cooled molecules, start to see differences whether you have a spin mixture or a polarized spin. spin polarized samples. And I'm using this as a prelude to give you the Alex Dalgarno's really far insight at the time. This paper that he was mentioning about with Bala at the time was, I think Bala was Alex's postdoc, yes. And this was in the 2001 when Alex was sort of witnessing remarkable experiments going on with ultracold gas here at CUA, MIT, Harvard Center for Ultracold Atoms. And so they've been thinking, Alex and his associates and postdocs and students have been thinking about what kind of a new physics or chemistry will come out of this. And in particular, I think this paper should be celebrated. What the paper is this? Well, it's actually this paper published in 2001 in Chemical Physics Letters. And they call it Chemistry at Ultracold Temperatures. I have another colleague, late Debbie Jing. If she was here, she wouldn't like that word ultracold temperatures. She will always correct me of saying, Jun, it's ultracold molecules and it's ultra low temperatures. Debbie is a very particular. She's just an amazing, amazing person. But okay, this is Alex's paper. And sometimes I'll say, Debbie, Alex wrote this way. And, but in this paper, Alex and Bala said, and this was really well before molecules would be brought to this ultra low temperatures, near absolute zero. And they were saying, well, the chemistry will not stop at absolute zero because this long duration of these collisions, the velocity are just really slow. These molecules are coming together, and they're just going through the tunneling process, through the repulsive barriers, and you will have chemical reactions. That was the prediction. The study they did was fluorine with a hydrogen molecule, and that's, I guess, is a very famous chemical reactions in chemistry, so that's why they started in this. For us in the laboratory, it's actually very difficult to cool down fluorine atoms or hydrogen molecules, so we started something different. But I just want to say, because of a paper like this, it created entire industry of cold molecules. There was people working on buffer gas cooling. We all know about John Doyle's pioneering effort. People were working on stark deceleration, magnetic field deceleration of molecules, the photo association, because the ultracold atoms was available. You can use the photons to associate the two atoms together to make a photo association. This was actually a review we wrote back in 2009. The field is now blossoming to include laser cooling, and I just mentioned it very briefly, evaporative cooling, sympathetic cooling, and now we have created a quantum gas of molecules, degenerate Fermi gas, degenerate Bose gas of molecules where the de Broglie waves of individual molecules' motional degrees of freedom overlap with each other. And creating just like atomic BEC, we can start to create a molecular BEC, molecular Fermi Cs, and so on. But that brings me back to just when Alex was writing that paper in 2001, we had Debbie at the time was very young, and I was even, I was the same age, but she was scientifically more mature than I was. She was 2 years ahead of me in terms of being a JILA fellow. She was hired 2 years before me. But then, of course, Eric Cornell and Carl Weinman, as you know, they shared the Nobel Prize in BEC. After that, Carl was the one who got a call from a foundation saying, well, Carl, do you want to do something different than atoms? And Carl Weinman actually approached us saying, we should build a new JILA cold molecule center. That's what Carl had this amazing vision. He's going to build a new cold molecule center. He said, 4 of us should work together. And Eric at the time was thinking about doing EDM. And in fact, he really shifted his scientific focus from BEC to EDM at that time. And I just mentioned that there's a new limit. And finally, after 20 years or so of effort. And what Debbie and I actually started to collaborate in 2003. This was the first table we put it in. Jun Ye was the student that was hired to do this experiment. And this is the Jun when she was, just a beautiful young girl at the time, still is. And the people who we assembled together as a group, and this was a picture taken in 2008. The reason we took a picture of 2008 was because from 2003 to 2008, there was no results. It was just a very difficult experiment. Conquin is smiling now, and Silke, Spelkus, and so on. But at the time, they were stressful because there was no results. And in 2008, there was actually results was just coming out like crazy. And finally, we had a breakthrough, and so you can see everybody smiling a little bit. The technique, in the end, that Conquin and Debbie and we all worked together, and together with theorists like Savantylena Katochikova and Paul Julian, they were instrumental in making this work, is the idea of, well, you create two degenerate quantum gas of atoms. You can be rubidium BeC with the fermionic atoms of potassium. You go through the so-called Feshbach resonance, where using magnetic field to tune the relative collision channels to be in resonance with behind the barrier and molecular bound state. And you can create this very, very fluffy molecule called Feshbach molecules. And if you can make two laser beams with a phase coherence, you can transfer from one quantum state of the Feshbach molecule into a deeply bound ground state of molecules, thus creating a degenerate Fermi C of molecules. At the time, it was not quite degenerate, Fermi degenerate. The T over TF was 1.4. But this technique now has been used by many, many labs in the world to create these molecular quantum gas. And it took us another, actually, 10 years to finally create a degenerate Fermi gas in 2019, where we were able to reach 30,000 atoms, molecules at a temperature of 15 nanokelvin. And nowadays, we have several different degenerate quantum gases, Fermi gas in MPQ, in USTC, as well as very recent success by Sebastian Well, creating the BEC of bipolar molecules at Columbia just this year. So I want to go back to Alex's prediction of chemistry will be interesting near absolute zero. And this is the particular chemical reaction, 2 KRB coming together and forming K2 plus RB2. Back in 2010, we started this chemical reaction because this is a slightly exosomic. This chemical reaction is actually allowed. And you can think of when the temperature is so low, near absolute zero, you really have to use quantum mechanical pictures to describe how molecules collide. And as I mentioned earlier, you are using so-called partial waves to describe this angular momentum, which is quantized between the two colliding particles, two colliding molecules. KRB is a fermion, because potassium, we use a potassium-40 is a fermion, rubidium is a boson. So KRB is a fermionic molecule. There is no S wave. You cannot have 0 h-bar angular momentum to describe two fermionic molecules coming together at the low temperatures. So 1 h-bar unit is the first angular momentum you can have, the so-called P wave. Associated with this angular momentum 1 h-bar, there's this centrifugal barriers. And the molecules at this centrifugal barrier for YO molecules is 5 microkelvin, but for KRB is actually 24 microkelvin, it's a little lighter. And so if we cool the molecules down to hundreds of nanokelvin, they would have to penetrate through this barrier, through the tunneling, to have chemical reactions. And this can all be described very beautifully. In fact, connects to the old literature of nuclear reaction, the neutron going through the reaction barrier. And it's exactly the same tunneling threshold behavior that Eugene Wigner used to write about. And this is the basic physical picture. And the temperature is way below the barrier. And you really have to describe this process as just this P wave process. And as temperature gets lower and lower, it follows this linear coefficient. The two-body rate coefficient of the reaction is constant times the temperature T. And this fits very beautifully with the theory models that Paul Julian and so on put together. A very simple model. Basically, you have a van der Waals potential, and you have this one barrier that you look at the threshold behavior of the P wave, and this exactly is this linear curve. So this was all nice. This, in some sense, Alex's insight about chemical reactions at absolute temperature really balls out. And when we turn on electric field, you can think of when you turn on electric field, you're creating anisotropy of this otherwise isotropic landscape, because electric field is going to align the molecules and they can collide head to tail, which will lower the barrier. If they collide head to head in parallel, they will raise the barrier. But the one that's lower the barrier allows the two molecules to come in and penetrate through the barrier much more easily. So as you turn up the electric field, the reaction rate went up by 2 orders of magnitude if you increase the dipole moment just by a factor of 2 or 3. So that's obviously not such a good news if the molecules are created in quantum degeneracy, but they are very quickly get lost when you turn on electric field trying to see dipolar interactions. So we had to solve this problem. In order to solve this problem, again, took us about 10 years to do this. The idea being, finally, we can confine these molecules in reduced dimensions, like 2D traps, where the molecules are living on these sort of a skating rink kind of a structure, a stack of pancakes. And then you use 4 rods and 2 plates to create a sophisticated control of electric field, where you can have electric field perpendicular to those planes or tilted with certain angles. And this gives rise to the idea that since the molecules are so cold, it's very easy to use electric field to orient them. And so as you turn up electric field, the molecules start to collide not head to tail, but they had to force themselves to collide side by side. And that allow you to really suppress the inelastic loss. This is the theory done by Gouvin Corminier and John Bone back in 10 years ago. But electric field turns up the electrical dipole moment, so the elastic collision gets enhanced. And you can get to a certain point where elastic collision is actually more than 200 times above the inelastic collisional rate. And this is a regime where you can finally do evaporative cooling, because elastic collision is where you are thermalizing these molecules. You can kick out the hot molecules out and leave behind cold molecules, and you can get into the so-called quantum degeneracy where you use T over TF. TF is the Fermi temperature. You can get below the TF, T over TF less than 0.5 or so. So this is all long dreams, how do you turn on dipole moment? How do you keep the elastic interactions between the dipoles alive without destroying these molecules? And once you can do that, I mentioned about strong connection between Cambridge and JILA and Boulder. Will Tobias was actually an undergraduate student from Conquin's lab. He came to JILA as a graduate student, and he did this experiment where we can create layer by layer of these molecules. You apply an electrical field gradient. Each molecule will be subject to different electrical field slightly. And because of the DC stock shift, the rotational states between 0 and 1 will be slightly modified due to the presence of the DC stock shift. And that means you can actually use rotational microwave spectroscopy. And that's easily done. You can go visit Mike's lab downstairs. And you can select individual pancakes of molecules now, addressing them 1 layer at a time. The separation between layers is just 400 nanometers or so, but 500 nanometers. But now you can select the one pancake, another pancake. Not only you can select pancake, you can also control which rotational state you want them to be. And in that case, this is the rotational spectroscopy. You can see one pancake, second pancake, third pancake. You can select any one of them. But now you can say, well, I can make a sandwich where the 2 outer layers, just a 3 layer of molecules, the 2 outer layers are in rotational state 1. The inner layer is in rotational state 0. So just as I described, I put electric field on these molecules are either aligned or anti-aligned with electric field due to their strong field seeking or weak field seeking nature of the rotational states. And the molecules can collide with each other through the so-called P-wave barrier that I was describing to you. So they can have a chemical reactions through the P-wave protected by the electrical field-induced side-by-side collisional barrier. But if the distance between layers are close enough, the molecules can have the so-called spin exchange interaction, where this molecule and that molecule now swapped their excitation. The molecules themselves are not tunneling. So the physical molecule is staying put, but their excitation, this one is rotationally excited, now can go down to the rotational ground, and this was previously rotational ground, can go to rotational excited. So suddenly, your homogeneous population has now been introducing some excitations which is different from the rest of your neighbors, and you can have S-wave collisions. The P-wave collision suddenly goes away, and you can have a much faster loss. So and we can actually watch this chemical reactions happening remotely, layer by layer, because of the molecules can hop back and forth. It's a purely quantum mechanical effect. And I think if Alex is here today, I think he'll be happy to see this. Not only you can watch the chemical reactions at ultra low temperatures, you can actually watch sort of a remote detonation of chemical reactions purely by quantum mechanics. You can prepare them in different superpositions of quantum states and watch how you can control the orientation, the angular momentum, the dipole moments, and so on to dictate however you want different chemical reaction rate to go. And actually on Thursday, as Hossein said, I'm going to give the third talk. I'm actually going to expand on this area where now that you can start to create molecular quantum gas layer by layer and bulk by bulk, you can turn on electric field. It will be fantastic. One area will be looking into, for example, pairing. Instead of having chemical reactions, we can start to look at possibilities of a pairing of these molecules. When 2 fermionic molecules pairs into a boson, or 3 fermionic molecules still pairs into a fermion, you will see some very strange quantum material where each individual pancake contains a Fermi C of the molecules, but then you have some ordering of these long sticks of the ordered molecules sticking around, colliding with the different quantum statistics. These are the areas which can connect to superconductivities, topological insulators, and physics like that. So not all the interesting sort of science with cold molecules have to get molecules to be such a low temperatures. You may be asking yourself, 100 nanokelvin, that seems to be ridiculously low temperature. My lab won't do that. And I want to show you some experiments where you actually don't have to go to very low temperatures, that you still see some very, very interesting emerging physics. An example I want to give is a C60 molecule. And during Brian's PhD time, for the first time, we were able to cool this molecule down just not by a lot, almost just by cooling down to like 100 Kelvin or so, kind of a temperature where all the vibrational degrees of freedom has been collapsed down to the absolute vibrational ground state. But there are still many rotational excitation that's happening. This one shows that we can, once you have cooled the molecule down to the vibrational ground state, you can put a photon in there to excite it into the first or second fundamental vibrational mode. This is one of the modes that we are studying at 8.5 micron. So these molecules these atoms are oscillating back and forth, has some quantum rotations associated with that. And these are the 60 bosonic C-carbon-12, so no nuclear spins. In the actually very interesting study, C13, you will have 60 spins that can potentially interact with the rotational and the vibrational degrees of freedom. So molecules like this, in fact, C60 is a very special molecule, has this very high symmetry groups called icosahedral symmetry, 120 symmetry groups. And it's really interesting because these are bosons, identical bosons, just as I was describing the collisional process of YO and KRB. You have to obey this so-called symmetry operations. For bosonic systems, when you interchange the molecular atomic positions or nuclear positions in this molecule, the operator would have to be symmetrical. And you have a lot of a symmetry axis where you can rotate the 2-fold axis, 3-fold axis with the hexagon, or through the pentagon, you have 5-fold axis, you can rotate them. And this gives rise to some really interesting consequences. For example, you have 6 different axes of pentagons, you have 10 different axes of hexagons, and now if you look at rotational quantum number you can have for such a molecule, the the rotational number is not from 0, 1, 2, 3, 4, 5. Rather, you have a ground state 0, and the next excited rotational state is 6. Because there's a 6 different axes where you have the symmetry of the pentagons. So if you go in to do rotational spectroscopy, you'll find it very strange. You will see J equal to 0, J equal to 6. Next one will be J equals to 10, and so on. At the time, and we're actually doing this right now, but at the time, we did not cool the system sufficiently low to be able to see these missing lines. But what we can actually do, in fact, is just look at the distribution of the rotational branch of the so-called R branch of these transitions. And I want to contrast the situation when before C60 was cooled down versus C60 was cooled down. We can start to see these rotational resolved quantum state spectroscopy signatures of the rotational degrees of freedom. And if you zoom in a little bit, you can see this intensity modulations on your rotational transition amplitude. And this intensity modulation comes as a consequence of the spin statistics of 60 identical bosons, gives rise to this modulation. And that's because the J is already very large. If you go down to J equal to 0 to 10, you will see actually some line will be missing completely. So this was giving us the first success of saying, well, that's actually interesting that for the first time we can do quantum state resolved spectroscopy of complex molecules with 60 atoms together. But what we noticed, of course, is that in the P branch, things look very, very strange, even though by theoretical calculation, R branch and P branch should look just very much the same. And so what's going on there? It took us 3 or 4 years to solve this mystery by doing better spectroscopy, just zooming in what's going on. And turns out this is basically the branch that we're starting to look from very low J's and start to look into is what's going on with each individual little hairy line. Is this actually noise or actually real signal? And as you can see, when the J number is small, you can see this rotational progression very regularly. But by the time you go to the middle region, like C and D panels, you can see each rotational line gets split into kind of a finger of the transitions. And if you look at the splitting patterns a little more carefully, by labeling them individual lines and look at record all the energy splittings and plot them out, a very, very interesting spectrum emerges. This looks like this is actually experimental data. Each data point showing this little finger that's being deviated away from the predicted rotational position as a function of the quantum number of the rotational excitation. So as you spin the C60 molecules faster and faster and faster, you can see there's a regular patterns of a deviation from the predicted rotational distribution. But the pattern looks chaotic. On the other hand, you can also see very regular at the same time. And it turns out you can completely reproduce this with a theory. And it's telling you fascinating sort of emerging phenomena of as you spin the C60 molecules faster and faster, they can spin around the pentagons or hexagons. When the pentagon rotation energy and hexagon rotation energy is completely different, they can be ergodic. They essentially can go through, because of the symmetry, you can be spinning around this axis, spinning around this axis. Remember I told you there's 10 hexagons and so on. So in the rank 6 spherical tensor sort of a product, look at the spherical harmonics, you have this massive symmetry there, and this is all the energy states can be accessed in an ergodic way, or which axis that you're rotating your molecule with doesn't make any difference. But when you are, for example, when you're rotating at a particular velocity, a particular angular momentum, where the rotation along hexagon or pentagon actually energy degenerate, but the hexagon looks different than pentagon. And this is in the regime where energy looks very close, but they cannot access each other's phase space. The system turns into non-ergodic. And if it's spinning faster, it becomes ergodic again. So this is really interesting. A single molecule like C60, you can go through, as you rotate faster and faster, you can go through this ergodic, non-ergodic, ergodic, non-ergodic again, looking at how much information of all these degrees of freedom being contained in that molecule, and that information is not being lost. They are actually still contained here. In principle, you can understand everything of the 60-atom quantum system. So The tool that we use to do this kind of a spectroscopy is the so-called frequency combs that I touched upon of yesterday of making atomic clocks and make optical frequency combs. And we can generate these frequency combs into extreme ultraviolet. And that's actually the place, not extreme ultraviolet, the mid-infrared and the long infrared wavelength for molecular spectroscopy. And so in this case, you can study a range of large size molecules, including C60 molecules that I just mentioned earlier. And this is actually really interesting technology because you have these very regularly spaced optical components. And you put the molecules on it, each component becomes a detection channel of a molecular absorption. So you can actually achieve very high resolution spectroscopy plus very broad bandwidth simultaneously. And this allows us to look at the molecules like a C60 and others. But I want to end my talk on giving you a little bit of an applied, sort of a little bit of a lighthearted discussion of molecular spectroscopy application. I thought it was fun to include, how fundamental physics connects to very applied research. This was completely inspired by a call at the beginning of the pandemic. People say, when you do comb spectroscopy, is it possible you can see COVID? This was in March 2020. And that's seriously, I got received a call from National Academy. A colleague knew that I was doing comb spectroscopy. And then program officer at the Air Force OSR said, Jun, I have been funding you, all these years. Can you do something useful now? And so this was like really triggered about this. We had this comb, and we put a comb through a pair of mirrors. That's what Brian did for C60 spectroscopy. And each one of the comb lines can be coupled into this fabric pearl cavity. What this fabric pearl cavity is doing is allowing the laser light of each individual comb light to bounce back and forth. And so that extends the interaction length. If the light missed the molecule from your breath, it has a chance to bounce back and forth 10,000 times to see it. So that increases the sensitivity. And then we have a technique to, after this rainbow of light interacted with molecules, you can have a way to disperse it out to one channel at a time simultaneously to see what information is missing. Well, that missing information is because the molecule have absorbed a photon from the comb. So use this. You can see immediately where that's going. If you have in your breath, and we collect the breath in a half-liter bag. You just breathe in once, and we collect that sample, and we turn this into molecular spectroscopy data. And in principle, this molecular spectroscopy data can be very powerful biomarkers to see a range of diseases. This has been promised for a long time. And I want to tell you, I'm actually more than confident now than ever that this is coming because of the big data. We actually tried to do something like this 10 years ago. We eventually gave up because nobody will tell you, if you had a lung cancer, what kind of a molecule is going to come out? You wouldn't know. Nobody had done this. People have studied a certain disease, and they will say, oh, if you have asthma, you may want to watch out for H2O2. But what you need is really a vast library of molecules coming out from your mouth with different possible disease and so on, being able to make a connection. And this, I just felt, that's impossible. Nobody had done that study. There's no book written. There's no library you can look for. But big data is changing this in a way that I've never imagined. So through molecular spectroscopy, a stroke of breath turns into just millions of experimental data points. Those are, and I'm comparing the experimentally detected line. These are experimental data versus the simulation of the various different molecules in that particular spectral region of something like on the order of 100 wave numbers or so. And we know in our exhaled human breath, of course, most of this atmosphere, but there are some very, very small amount, less than 1% total. If you look into, there's ammonia, there's methanol, there's nitric oxide, the formaldehyde, and hydrogen peroxide, and so on. Typically, the concentration at parts per million, parts per billion, and sometimes parts per trillion level. And if you can see all kinds of molecules at once, well, you can imagine you can start to build a barcode where different species have a concentration rise or fall depending on particular health conditions you may have. And if you can keep track of all this with machine learning, that seems like it will be a very good health barcode to maintain. So the lesson is that we want to detect as many species as possible. And the frequency comb gives you that tool. When we set up the study for COVID in 2020, and it took us a year to finally get all the approval for IRB and so on. That was silly, but for human subject, it's unlike physics. You have to get all these approvals, and that takes a long time. So if you want to study like this, you maybe get approval first. But we finally got this going, you can have, at the time we only had a mid-IR comb at a 3.5 micron. We now have a comb from 3 to 6 micron. 3 micron worth of spectral band was being collected at once. So you can see thousands of these molecular species coming through with this cavity buildup. And what you need is to figure out how do you connect the molecular spectroscopy of each person's breath to a medical condition. And we initially just did our own little machine learning with this so-called partially square analysis. And the idea is you have lots of information coming out on these individual molecular lines. Is it possible you can do some diagonalization, this principal partially square analysis, to separate, say, COVID positive from COVID negative to be as big a distance as possible through some artificial axis of the optimized combinations of 10 lines here, 3 lines there, or 5 molecules here, 5 molecules there, that allow you to separate distance between the positive and the negative case. So you can make a diagonals. These are positive COVID people, these are negative COVID people, and so on. And this will depend on how the machine learning will tell you what are the principal components of these axes will be. And I'm showing you just a 2-dimensional, but of course this can be thousands of dimensions because you have each molecular line in principle can tell you the positive versus negative. And so I want to just go through this rather quickly. The comb spectroscopy from the breath, it turned into, in this particular case, 14,000 channels. We have 14,000 individual data points immediately within a few seconds. When you breathe in, we already know that information. And you can turn this, the first time we did it, because we were molecular spectroscopists, we immediately connect these lines to particular molecules that we know of. And then from the molecules, we can say, okay, there's a certain amount of ammonia, a certain amount of formaldehyde. We can use this to do machine learning based on the concentration of different molecules and make a prediction of whether you have COVID positivity or negativity. And this is the so-called molecular-based approach. But then you talk to real true machine learning specialists. They said, you're completely wasting your time. This step is a really bad step. Yeah. You're already laughing. Yeah, and I didn't know this, of course, because I really didn't believe in machine learning. Like showing my, being a prejudiced. And you just have to be open-minded. Absolutely have to be open-minded. They said the best way to do it is forget about these molecules. Just go directly into the line. You want to see, and later on we just find how powerful this is, because these are the lines that we can see, but in the background, there were unresolved lines. There's features on there. And those features, in principle, they are all the useful information you can ask a machine to learn, instead of connecting to molecules, because that knowledge is limited to begin with. So this is so-called a pattern-based approach. So we learned all that, and finally we went into the university. We collected 200 students, asked them to donate their breath. Each gets a $50 reward for donating a breath. And so people actually were interested, very interested in what. So we got 200 samples, and we divided into 100 samples that we're going to do the machine learning. Another 100 samples to do the testing. The 100 sample, we know who's positive, who's negative. We fed into the machine. Afterwards, we have another 100 students. We did not tell the machine whether these students are positive or negative, and the machine had to make a prediction and to check with the PCR test. And this actually shows the curve. This, from medical science, they have a very, very creative language called area under the curve. This is literally what they do, AUC, area under the curve. And the thing you probably have heard through the COVID pandemic, the so-called the false positive rate, true positive rate. You want the sensitivity to be really high because if you are positive, I want to detect you, you are positive. You want this to be 1. The false positive rate, well, if you are negative and detect you as a positive, that's obviously bad, and vice versa. So I want this false positive rate to be 0. So in principle, you want this curve to be 100%, like here. This should be like 100%. I was told no medical test has that. The best area under the curve is on the order of 96%, and that turns out to be pregnancy test. That's the best test you can have if you are positive or not positive negative. If you're pregnant or not pregnant, they can be pretty certain. The PCR test for COVID is 92%, and we use the PCR to train our machine, and that got to 85% accuracy. So in fact, we are actually limited by PCR because if PCR was wrong, we are training our machine to be wrong. But this is actually, for medical science, anything above 80% is considered excellent discrimination already. And this is the first trial with 200 students. You can argue you don't have enough samples. You need to go for thousands. And that's really something we want to do now. When COVID started, I had one graduate student who was working at the time with Brian when Brian was leaving. That graduate student was a new student, Qizong. But he turned out to be just amazing. He built all these OPO frequency combs. He learned the machine learning for himself. And we got all these 200 students enrolled, and we did this, published the first medical journal paper in our scientific career. And now the medical doctors from Denver Children's Hospital start to connect with us saying, oh, actually, can you study COPDs or asthma in children? Sometimes they are triggered by bacteria infection. You have little kids coming into doctor's clinic. They are sick. The parents are really worried. And the doctors, if you have kids, you will know that doctors don't know why they are sick. They wouldn't know whether they have bacteria or virus. That's the first thing they don't know. So this Children's Hospital, Lillian, she's the director of research at the Denver Children's Hospital. She said, if the comb can tell you whether a child is bacteria or virus, would it be a big deal already? And that will really change people's lives, because you can come in and breathe, and you will say, okay, you go this treatment or that treatment. So that's what we are doing right now with sort of a children's asthma problem. And we hope that this will have a big thing. The reason why I want to be positive on this is when we started the COVID work, Qizong put together a very simple system, was already working in the lab. He just had to learn machine learning. And this is the spectrum that we covered. I think, yeah. So it's about 140 wave numbers or so. And if I zoom in a little bit, you can see there's a faint, that's what I was looking for. There's a faint area that's showing you that this is about the spectral window that we were using to do COVID detection. And now you can see very clear that's about this area that we were doing the COVID detection. But now we actually have a frequency comb that covers the entire window. And so this will be, I actually think with the machine learning, if there were human eyes, you get tired looking at these lines. But machines don't get tired, and they have this incredible power. So now imagine you can have all these molecules being detected by the comb spectroscopy. And we just started with COVID in this very narrow width of the spectrum. So hopefully, with this extended coverage with real medical doctors telling us that, yeah, this children is definitely sick, this child is not sick, we can use this to train our machine and really look at whether you have a bacteria or virus, and finally go in and make a difference, in people's life with a comb spectroscopy, which is supposed to be coming out of atomic clocks and quantum technology. We want to call this shamelessly as a quantum technology that's making an impact for life science. So with that, I want to end my talk here. And on Thursday, I'll talk a lot more about the spin models that's done by this set of graduate students and postdocs. Qizong. It was a graduate student trained by Brian Changala, but he's not a hero of doing this COVID detection and medical science. This is the EDM collaboration. Eric Cornell's laboratory is really pushing forward on the setting new limits along with Acme and so on. And the C60 I briefly mentioned, headed by Li Liu, Dina Rosenberg, both postdocs, and it was a collaboration of David Nesbitt, and his name used to be here, but I'm sorry that it's not quite here. And the YO cooling experiments done by Justin Peru and Cameron. Thank you very much.
Fantastic talk. Questions? John?
Thank you very much for this very inspiring talk.
Oh, thanks.
So my question is about like how you build the molecules atom by atom with the phase one resonance.
Yes.
Them down. So I wonder how like generic this process is. Is it possible to make more complex molecules this way, for perhaps repeatedly using it and then growing it? Is that a possibility?
Excellent question, actually. So we studied with KRB. Turns out now any bioalkali species, any combination of bioalkali, you can make molecules. So these are two diatomic molecules. These are diatomic molecules still. People are now trying to work out towards the column number 2 in the periodic table, where you can have a bioalkali with alkaline earth atoms. They're connecting together to make a molecule. There are new work that's coming out, very new, like this year, last year. Wolfgang Ketterle's group, for example, in MIT, start to see molecule-molecule collisions, and like Feshbach resonance, perhaps. These are the first step, as you said, exactly right. You did this one step, you created this associating. Well, now you have 2 of them, like a building block. Maybe you can do the next one. It's like a Lego, going to the building more complex tetramers and so trimers and so on. And there's a group in USTC and a group in MPQ. They are already creating triatomic molecules with this technique, atom and a molecule forming a triatomic molecule. So it is very interesting how not only you're doing quantum science with these diatomic molecules, but you can potentially shed more light in quantum chemistry. Imagine one day we can conquer the laser cooling even further. We can cool oxygen atoms, cool carbon atoms, and bring them together, make a CO molecule. No, the possibility is endless. It's the reason why we cannot cool fluorine. If we going back to Alex Dalgarno's initial paper, is because we don't have those lasers. Polar UV lasers are very difficult technologically. But if we make breakthroughs on these technology, those scientific landscape will be opened further.
I wonder if this question will turn out to be related. I'm curious about the pancake traps that you described.
Yes.
Coming from more of an engineering standpoint, I'm curious how exotic you can get, even in theory, for designing these traps and how this might affect.
Yes. You're asking how you can, for example, arbitrarily creating landscapes. Yeah, so I just talked about pancakes. Of course, what you can do is you start with a crystal, with 3D, 3 sets of laser beams, creating those 3D crystals. And then you can turn down the intensity in the other 2 directions, such that you create pancakes. 3D can also turn into cigars. You can have molecules in particular cigars. You can look at the molecules in 3D. And now you heard about tweezer that Confining and John Doyle are doing. There were experiments in Paris. They created Eiffel Tower of atoms, 3-dimensional structure. So imagine, I talked about C60. C60 natural bone, just really beautiful molecule that's already there. But imagine you can use techniques, as you are alluding to, you can use optical tweezers and make a 3-dimensional structures of these molecules.
Can you start to think of this almost like additive manufacturing at the level of individual molecules?
Yeah.
Like a 3D printer.
Yeah, in principle, that's right. And at Conquin's lab, even, I think they had a science cover. They were saying they can watch the chemical reactions of 1 atom per 1 atom at a time. And these are new age of studying chemical reaction. You're putting 2 molecules or 2 atoms and watch them how they react and so on. And what you're alluding to is once you have that kind of a capability, you can build up complex structures from it. But you needed these, like you have to remove all entropy first before you can add entropy in a controlled way.
Other questions? So there are now efforts, Doc, well, maybe you'll ask and I'll mention it. Yes, go ahead.
Well, no, I'm just amazed that you could train the machine learning for the COVID detection on only 200 samples.
Yeah.
Because if you even at the limit where a linear algebra problem, which it's not quite, but you have your linear combination of all the different molecules giving you the spectrum, you have to marginalize over all these differences of the different samples that
Yes.
have nothing to do with COVID.
Yes.
And it seems like you would need far more than 200 samples to do that. So the fact that you managed to get your AUC that good with only 200 suggests this is a very promising.
And the population is a little homogeneous. These are all young students, Boulder campus.
That probably helps.
Yeah, it's in some sense we opened it up to any students enrolled at CEO Boulder, but of course most students are in the age of 22 something, another thing I was going to say is I think there's what you're alluding to is a very complex problem. Like you're coughing, that coughing may have nothing to do with COVID. It's like something else. Sure. So we actually ask people to fill in their spreadsheet when they say, I got a COVID positive test. We ask them, do you have an abdominal? We ask a bunch of other questions. And in fact, it's really interesting. So you can say COVID versus no COVID. You can study that. You can also study did you ride bus this morning versus you didn't ride the bus this morning? And we'll see the curve is exactly 50%. Like there's no correlation.
Good.
And so I know it's interesting. We even ask them to write down your gender, male, female, and we can tell difference.
That's amazing.
And it's not AUC of 84%, it's a 64%, so it's nowhere close to be accurate, but you can actually see the curve bumps up. And there's different things. So I think the machine learning in principle can, depending on how you collect your data, do different bifurcations. Mm-hmm. Because the sample might have multiple inferences on multiple parameters, but if the machine can, if you ask one question, like, did you have abdominal pain versus did you drink alcohol or you didn't drink alcohol, that absolutely can be detected, even though they have nothing to do with the COVID. So that you can have a different access to dissect your data. That's the beginning. I actually personally would say 200 samples are way too little. In order to, so don't think of me as another, what's her name, Holmes? Warm blood solves all the problem. No, I'm not promising this. We need far more data. And I have, being a NIST employee, I cannot make money out of this, so I have no money pressure. We just want to take the study and see what kind of a promise this can bring. It's a very early stage.
I hope the grant paid for that $10,000 you paid.
The Air Force officer was extremely happy. In fact, he said, "Do you need another comb?"
My question relates to the laser cooling. So I think there is sort of efforts to actually maybe use laser or cool molecules, cold molecules, to create by dissociation effectively cold atoms, which would otherwise not be able to naturally trap and cool.
That's correct, yeah. So YO, for example, is an example, or calcium fluoride that John Doyle works on is an example where you can't cool the oxygen or fluorine atoms yet, and you cannot do this association. So the idea of laser cooling is give you more chemically diverse species that you can actually bring to the quantum regime. Another thing that Wolfgang said very well was, by alkali, we kind of cheated our way. The atoms are already cold, and we just associate them. Molecules, where you have direct laser cooling, you actually have to figure out all the pathways of doing photon manipulation. But once you figure that out, in fact, then it turns into your advantage, because you can then read that molecule really well with all these photons you already have. So there's always those pros and cons. Science always goes along that, how naturally it grows.
One more question.
This is maybe more of a, where you leave me thinking in terms of space, the future of space systems. I imagine,
Astrophysics.
space, planetary science, astrophysics.
Yeah.
Imagine a future spacecraft that has a very high precision atomic clock, maybe also one of these combs, maybe also very advanced onboard machine learning. What could you imagine for what we might be able to achieve scientifically?
Well, NASA, 10 years ago, maybe more than 10 years ago, they had, I'm now speaking out of my depth because they are real experts here who actually do real astrophysics with molecules. But let me attempt answer, and then we can have Mike or people like that to chime in. But NASA at one point want to build a comb to carry with them to go to Mars. And you can do these incredible spectroscopy and understand the entire atmospheric composition of Mars, for example. The spectrometer based on ionization of samples, which are the tool of the trade that people use already, very mature technology. But the comb is coming up. You need to make sure these combs survive in these deep space flights. And these are optical instruments. For me, working in the lab, you have your hands, you can tweak. But now you're in another planet, you wouldn't have that capabilities. But I do think, coming back to astrophysics side, the major scientific discoveries are coming from astrophysics. We can talk about trying to see EDMs and so on. And it's true. As the precision advances, we may be able to help discover fundamental symmetries and so on. But I think the most exciting scientific discovery in physics realm mostly are coming from astrophysics observations and so on. So if we can help building better tools to help astrophysics, I feel that we are fulfilling our duty. And so this is a big question. What kind of tools astrophysics exploration will need? Maybe microwave spectroscopy is what you need. Maybe the optical technologies where you can link satellites, you can take images from very far distant galaxies. You have such a high sensitivity, just a few molecules in the intergalactic medium, you can pick them up and so on. So these are the areas I think will be, in my mind, very exciting connection between AMO, tabletop quantum science to big science like astrophysics. I didn't really answer your question in an intellectually deep way, but I think hopefully you see my positive attitude towards it. Mike, you want to chime in?
No, I think it was good. It's good.
So if there are no further questions, I think this is actually a very high note to sort of join me in thanking Jun for a very beautiful And for those who are interested, the third lecture will be Thursday at 10 o'clock Pierce Hall. Here's where you want. It's on the web. Apparently coffee and whatever. Okay.
Yeah,